What's going on, everybody? I'm Za.
And I'm Grady. And today we're going to be talking to you guys about black holes, specifically what is a black hole, who discovered them and when, and then also discuss a little bit about what we don't know about them.
So to start off, a black hole is a region of space where the gravitational force is so strong that nothing, not even light, can escape it. And the boundary around a black hole, beyond which nothing can escape, is called the event horizon. Once an object crosses this event horizon, it is impossible for it to leave the black hole. The center of the black hole is a point of infinite density, known as the singularity, where the laws of physics as we know them begin to break down. Black holes form when massive stars run out of fuel and can no longer support their own weight. As the star collapses under its own gravity, it becomes denser and denser until it becomes a singularity at the center of the black hole. The size of the black hole is determined by its mass. The more mass of the black hole, the larger its event horizon. Black holes come in different types depending on their size and properties. The most common type is a stellar black hole, which is formed from the collapse of a single massive star. There are also intermediate black holes and supermassive black holes, which are found at the centers of most galaxies, including our own, the Milky Way galaxy, and can have masses millions or even billions of times greater than that of the sun.
And then to talk about who discovered them and when, the concept of a black hole was first proposed in the early 20th century by the German physicist Karl Schwarzschild, who was working on Einstein's theory of general relativity. And in 1916, Schwarzschild found a solution to Einstein's equations that described a region of space where the gravitational pull was so strong that nothing, not even light, could escape. However, it wasn't until the 1960s that astronomers began to find evidence for the existence of black holes in the universe. One of the pioneers in this field was a physicist named John Wheeler, who actually coined the term in 1967. And Wheeler, along with his colleague Robert Oppenheimer and Hartland Snyder, published a seminal paper in 1939 that laid out the theoretical framework for black holes forming from collapsing stars. And then in the years that followed, astronomers began to observe the effects of black holes on nearby matter, such as stars and gas clouds. One of the most famous early examples was the discovery of a binary star system called Cygnus X1 in 1971, which showed evidence of a massive object pulling material from its companion star. And since then, astronomers have discovered many black holes throughout the universe, both through their gravitational effects on nearby matter and through the X-rays emitted by matter that falls into them.
So to go back to what we were talking about earlier, kind of related to the size of black holes, the size is determined by their event horizon, which is the boundary beyond which nothing, including light, can escape, as we said before. So going off to the size of black holes and a little bit more about them, there are two kinds, a rotating and non-rotating black hole. For a non-rotating black hole, the Schwarzschild radius is given by the equation R equals 2gm divided by c squared, where R represents the radius of the horizon, g is the gravitational constant, and m stands for the mass of the black hole. C is the speed of light. So if you take a black hole with the mass of 10 times that of the sun, it will have a Schwarzschild radius of approximately 30 kilometers. This means that any object that gets within 30 kilometers of that black hole will be pulled in and never able to escape again. For rotating black holes, however, the situation is a little bit more complex, as they have an additional effect known as frame dragging, which causes space-time to twist and warp around them. This kind of results in a more complicated shape for the event horizon, known as the ergosphere, which can extend further out from the black hole than the Schwarzschild radius. So basically, as the object gets closer, the gravitational force of the black hole will become stronger, and eventually it will become so strong that it will just pull it directly into the black hole, and this process is known as the spaghettification, because the object will be stretched into a long, thin shape resembling spaghetti.
And then to finish off with what don't we know about black holes. So despite decades of research and study, there's still much that we do not know about black holes. One of the biggest mysteries being what happens at the center of it, known as the singularity. At the singularity, the laws of physics as we know them break down, and it is impossible to predict what happens. Some theories suggest that the singularity may be a point of infinite density and curvature, while others think that it may be a gateway to another universe. For example, we do not know exactly how this collapse proceeds, what triggers the collapse, or how the matter falling inwards interacts with the surrounding environment, partly because the conditions in the core of the collapsing star are extreme and not easily simulated in a lab. And lastly, there's also an ongoing debate about the role of other factors in the formation of black holes, such as the presence of magnetic fields, turbulence, and rotation. Some suggest that these factors could play an important role in shaping the properties of black holes, but contributions are still being studied. Basically, in short, while we have made significant progress in understanding black holes, there's still much to learn about these mysterious objects, and the study of black holes remains an active and exciting field of research in astrophysics today.